Good afternoon and welcome to this very special INFOSYS-ICTS Ramanujan lecture series. This is part of our flagship lecture series in various disciplines. We have the Ramanujan series in mathematics, the Chandrasekhar series in the physical sciences, the Turing lecture series in computer science, biology, engineering, and related disciplines. The Infosys Foundation has been very generous to support these lecture series as well as the associated discussion meeting, and I'm very grateful for their support. And in addition to these, we have a number of other special lecture series, and if you don't know, you may have seen the announcement. Tomorrow we are launching a new series called the Madhava lecture series, after the 14th century mathematician Madhava of Sangamagrama. This will be very appropriately on Madhava himself. The inaugural lecture series will be on Madhava, the mathematician, and his work. And it will be delivered by Professor P.P. Divakaran, formerly of the TIFR Mumbai, who has recently written a book on Indian mathematics. And so I invite you all to come. It will be over here, and I believe the schedule of your discussion meeting will allow you to come for that. So let me extend that invitation. The only thing we couldn't do is, because of the large number of people, we couldn't hold the Madhava lecture series on Madhava in the Madhava auditorium. It will be instead in the Ramanujan auditorium, but yes. So I think I will now invite Professor Pranav Pandit to give an introduction to Professor Carlos Simpson. And let me also extend my thanks to Professor Simpson to agree to give this lecture series here. In fact, I think he is giving a very heavy, I think the organizers have imposed on his kindness to give a very detailed course on moduli spaces. So we are looking forward to the inaugural lecture. Pranav.
Yeah, thanks a lot, Rajesh, for the introduction to ICTS and the Ramanujan lectures. And yeah, you're absolutely right. We're making Carlos work very hard indeed. Thanks, Carlos, for accepting our invitation and doing that for us. So I think for most of you, Carlos needs no introduction, but this is the first talk is meant for a broad audience, including non-mathematicians. So let me begin by giving you a short introduction to Carlos and his work. So Carlos did his PhD in 1987 from Harvard under Wilfried Schmidt. And then he was, after that, an instructor and assistant professor at Princeton till 1991 when he moved to France. He has been the director of the research at the CNRS, first in Toulouse till 1999, and then in Nice, where he is now. Carlos is one of the most diverse mathematicians I know. He's done work on a broad range of things. This conference is on algebraic geometry. He's done work on, fundamental work on non-abelian Hodge correspondence, which he essentially created following the work of Hitchin, which relates topology on the one hand, character varieties to algebraic geometry and homomorphic data like Higgs bundles. And that has given rise to a whole area of mathematics, which you've heard a lot of talks about already. You've heard a couple of talks at this conference this morning. And Carlos has also worked on higher category theory, I believe motivated originally by the non-abelian Hodge correspondence. He has a book out on higher category theory now, which is a very huge book, more than 400 pages, I think. And he has worked on computer theorem proving using Coq and various other things, so ranging from the geometric Langton's program to homological mirror symmetry related mathematics. He's currently working on the Donaghy-Pantev approach to the geometric Langton's conjecture, and also on certain aspects of Fukaya categories and stability conditions on them, which is related to spectral networks and ideas from string theory. So, currently he's the chair of the Interdisciplinary Center for Artificial Intelligence at the Côte d'Azur. Is one of the chairs, and he's working on using artificial intelligence to understand the classification of algebraic structures like semigroups and finite categories. And we'll hear more about that from him on Friday when he will tell us about the use of artificial intelligence to understand moduli spaces. So I could say a lot more, but in the interest of time, so I'll stop there and hand over the floor to Carlos. And before that, we have a small...
We have a small ritual, a small ceremony for which I will invite Professor M.S. Raghunathan, who we are lucky to have here in our audience, to come and hand over on behalf of ICTS Sandalwood Buddha as a memento to Professor Simpson.
Thank you very much. Great honor. Thank you. Yeah. Thank you very much.
Okay, so sure.
Yeah.
Okay, thank you very much.
It's a great honor.
Yeah, and now the floor is all yours.
Okay, so thank you very much. This is a great honor to be invited to speak on moduli space theory in India. So I think thinking back to my time in graduate school, I think India has to be the country that by far furnished the greatest number of authors of papers that I was reading when I was learning about moduli space theory. Just sort of a wide range, as you all know, I think. Just a wide range of really original papers and things like that, which I don't think I'll be able to say all of the people, but I'll maybe try to say it along the way. So this is a great honor, and so it's a great pleasure, and thank you to Pranav to organize this meeting, which is very interesting. It's a great pleasure to see old people, see old friends, and to meet new people. Okay, so I'd like to start over here. Okay, so today I'd like to discuss just the general starting points for the theory of moduli of vector bundles and related structures. Okay, so I think everybody would agree that really the initial point of this theory is the paper of Narasimhan and Seshadri. It's too bad that Professor Seshadri was not able to make it. That would have been very nice. And Professor Narasimhan it's very nice that he's here. He's excused for today because I think, as you'll see, he knows everything everything I could possibly say about the subject today. In any case, okay. So I'd like to start. So let me just start by recalling some definitions. So we have a choice of letters for our curve, but let's have maybe X. For now, it's going to be a smooth projective curve over C, and then later could be a higher dimensional variety. Could be higher dimensional quasi-projective later. I mean, quasi-projective, not really, but with some kind of compactification. Now, what about so let's sort of confuse. We'll identify the analytic and algebraic varieties. So we also have the C infinity manifold, which we'll also call X. Okay. And so our first order of business is to talk about what's a bundle over X, okay? And let me also say that, so as we heard this morning, there are very interesting and subtle questions which arise when you, in fact, this sort in two talks, which arise when you start looking at general groups. But for us, G is really going to be probably GL R, or maybe SLR. Well, or some other group, but probably. To make things simple, I think you can hear in some other talks the more subtle problems with principal bundles for other groups. But so let's just discuss what's a bundle over X. So let's just recall that this means that suppose we cover X by open sets. So they're probably usually open sets, although they could be Zariski open sets. Then a bundle is given by gluing together bundles of the form UI cross C to the R. Using a gluing cocycle, Gij. Okay. So Gij is going to be a function from Uij, which is Ui intersect Uj, into GL R, C, let's say. And then we can use this cocycle to glue together these bundles over the open subsets. And so we should have Gij composed with, let's say, maybe Gj composed with Gij equals Gik on Uijk. Okay. And now the Gij can be various different types of functions. So so the case Gij is just a C infinity function. Then we're going to get a C infinity bundle. If it's a holomorphic function, then we're going to get a holomorphic. If it's an algebraic function, and let's say the Uij or the UIs are Zariski open, then we'll get an algebraic bundle. Okay. So we can see as we go up, if we have an algebraic function, it's holomorphic. If we have a homomorphic function, it's C infinity. So that means if we have an algebraic bundle, we can think of it as a homomorphic bundle or a C infinity bundle. Okay. And maybe I ran out of room here, but maybe one of the important cases is Gij locally constant function. Then we get a flat bundle or local system. So in a local system, there's a number of different ways of thinking about this, and I'll be discussing a couple of them in a minute. But let me just say, before getting to that, we can also think of local system as a locally constant sheaf. I wasn't very precise about what this really means here. So this is some kind of bundle over UI in the category that we want to consider. In the case of a constant thing, we could just take the constant sheaf over UI with values CR. When we glue those together, we get a locally constant sheaf. So that's probably what, technically speaking, we'll mean by the terminology local system. Okay. So again, if you have a locally constant function, then it's also algebraic. Well, it's at least holomorphic, and it's a C infinity, maybe not algebraic yet. But it also has the property that its derivatives are 0. And that allows us to give a connection. Okay? So if we have one of these things, then we get a vector bundle, either holomorphic or C infinity, with a flat connection. Let me explain more about that in a minute. Okay. So now the next thing I would like to say is the Serah's Gaga theorem. It says that the category of holomorphic and algebraic bundles are equivalent. So if you have a holomorphic bundle, it comes from a unique algebraic bundle. And this is important in the context of what we just said here, because here, if we have a locally constant collection of transition functions, those are probably not going to be on a Zariski open cover, otherwise the whole thing is going to be trivial. So that's going to give us a holomorphic bundle. And if you'd like to get an algebraic bundle, then you should apply Serah's Gaga theorem. And furthermore, if we have a holomorphic flat connection nabla, then we get an algebraic nabla. Okay. So these are the basic kinds of bundles that we'll be looking at. So a large part of what we'll be talking about is concerning the question of flat bundles. But before I get to that, let me just talk about the other main subject of discussion, which is moduli of holomorphic bundles. So we would like a moduli space What does that mean? It means a space M that parameterizes isomorphism classes of bundles. Okay. That's just like a general idea, okay? As we'll see in a minute, though, that's not in general going to exist. So then it turns out that we need we need to impose some conditions on the bundles, in order to have a moduli space that exists. And typically this is called semi-stability and semi-stability. So the notion of stability and semi-stability came up, I mean, among the first places that it came up was the paper of Narasimhan Seshadri, maybe, I guess, at around the same time also in the work of Mumford on GIT. So what I'd like to mainly concentrate on today, if I hope this is about the right level of thing to concentrate on, is to try to explain through a number of different illustrations sort of why we have the condition of stability. Okay? So, I mean, you know, the paper starts off always with, you know, we define what's a stable something or other, and we do the moduli space and so on. But I mean, how do you decide that we need this notion of stability? Okay, and I think that's something important for when you're starting out in the theory, at least. And I hope it might possibly be interesting for people who are in the theory for a longer period of time, at least to sort of go back and recall some of the basis for what's going on. Although I understand, of course, that for the experts, this is already very much known. Okay, so that's going to be sort of our main concern today. Okay, so let's turn to the first example. So the first example, which really explains why this is not just going to work as we said here. Okay, so the first example. I'll try. It's the case of x equals P1. Okay. Now we have Grothendieck's theorem, so says that any bundle which is either holomorphic or algebraic over P1 is isomorphic, is given by E It's just a direct sum of line bundles, of the standard line bundles O of n. Okay. So you might say, okay, this doesn't look very interesting, so maybe we can go on to a higher case or something like that. But I think we should look at this for a minute anyway. In view of the question as to whether we have a space that parameterizes isomorphism classes of bundles. Okay. So let's look in particular, so let's make an example. So we can make a, sorry. Okay, so there exists a family of bundles which, so E0, so parameterized by T in A1, let's say. So E0 is O of minus 1 plus O of 1, and ET is equal to O plus O for T different from 0. Okay. What's the construction, I guess? What is the construction? Exercise, okay. Okay, so what does this tell us? This tells us that, that if we had a moduli space, we would get a map from A1 into the moduli space, which sends T to the point O2 for T different from 0, and sends 0 to the point O of minus 1 plus O of 1. Okay? Well, that can't happen if the moduli space is a Hausdorff space, right? Because all the points go to one point, and then it jumps, and the other one goes to a different point. Okay, so then M could not be Hausdorff. Okay, so this tells us right away that we're not going to be able to answer this question. This is moduli space. We're not going to be able to answer this question in full generality to have a nice, at least not a nice space. Okay. So you might say there was an approach at the time, so Artm's approach. Maybe at the time or maybe slightly later, but is to sort of throw out the idea of a space Yeah, this can be completely algebraic, yeah. So Artm's approach was to replace the idea of a space by a stack. And in that case, so then there's going to exist a moduli stack of all bundles, but it's not going to be separated in any way, so highly highly non-separated, and furthermore, even if we fix the degree of the bundle, for example, this is degree 0, you can see we could take O of minus n plus O of n for any n. So there's infinitely many possibilities. So it's also not of finite type. It's only locally of finite type. So that's one approach, and it's an approach which is very often used and very often useful. Okay. But it doesn't directly, at least, doesn't directly give the geometric information we would like to have. Okay, so now, so if we examine what's going on here a little bit more, we can see this is you might say this is the bad point maybe. I mean, one of the two is the bad point. But this one looks like it might be the bad point because there's infinitely many of those going off in the direction of O of minus n plus O of n, so we maybe suspect that's probably going to be one of the problems. So if we look at this bundle, we can say, okay, this bundle decomposes into two different pieces that look different, okay? There's O of minus 1, it's a negative curve piece, and O of 1, which is a positive curve piece. So the first question you might ask is, to what extent is this decomposition going to be unique, okay? And then, so if you look at that a little bit, then you think, so what are we going to do? Okay, let's take sections of the bundle. If we take sections of the bundle, there's no sections here. And this has two-dimensional space of sections, okay? So if we look at sections of the bundle, then that's going to automatically pick out this subbundle, right? The bundle generated by sections of the bundle is going to be this subbundle, not this one. And if you look a little bit more, you can make an automorphism of the bundle. So there's no maps from this one into here, because you can't map a positive degree line bundle to a negative degree line bundle. But you can map a negative degree line bundle to a positive degree one. I mean, there's maps from here to here. The space of maps from here to here is the sections of O of 2. There's a three-dimensional space of sections. And any one of those sections has two zeros. It's a quadratic form, okay? So there's lots of maps from here to here, but no maps from here to here. And if you think about what that means for automorphisms of the bundle, it means that you can make automorphisms of the bundle that modify this piece. Okay? You can make a matrix of automorphisms that looks like 1, 1, some f, 0, such that this first piece moves around by a map from here to here. Okay? So the conclusion is that this piece is not unique, but this piece looks like it is unique. Okay, so the O of 1 the unique subbundle is the O of 1, so it's the higher degree bundle. Okay? And so this is generalized, so the generalization is called the Harder-Riemann filtration. So what does that say in general? Well, I haven't really gotten to the definition yet, but what it says is that any bundle E has a unique filtration such that let's call this F0. Such that the subquotients of the filtration are semi-stable. Sorry, I haven't defined this. We'll define this in a minute. I think almost all of you know what it already is. or semi-stable of some slope mu I, and the mu i's are bigger here and smaller here. So mu I plus 1 is strictly smaller than mu I. So that's just the generalization of this observation that we have. We take the highest slope, the highest degrees, roughly speaking, subbundle. Then you can make a filtration. I mean, here there's just 2 levels of the filtration. So this is a first example of what I would call an intrinsic motivation for the notion of stability. Right? The notion of semi-stability shows up naturally if we try to formalize this picture here. Okay? Try to formalize this picture here, then you naturally get to the notion. If you say, okay, what property do I want my bundle to have? You want to look at the bundle that has the highest degree. Okay? But if you play around with this a little bit, pretty quickly you understand that it's not really the degree that counts, it's sort of the relative amount of degree per unit of rank of the bundle. Okay? Let me maybe recall just the let me just recall the formula for the number for the space of set for the Euler characteristic, right? For line bundles, it's degree d plus 1 minus g. For vector bundles of rank r, it's degree d plus r times 1 minus g. So if you homogenize this term, you'll have to divide by the rank here. Okay. So let me just define the slope. Okay, the slope. The slope of E is mu of E, which is the degree of E divided by the rank of E. We can give the definition of semi-stable. As I said, everybody gives the definition of semi-stable without really explaining why, but I'm trying to explain why. So we say that E is semi-stable or stable if for all subsheaves the slope of the subsheaf is less than or equal to the slope of E. For stable, the subsheaf should also not be equal to E, obviously. Okay. This is, of course, slope. Semi-stable, slope stable. Okay. So if you try to build this, so let's not do this too much any further here, but if you try to build up a filtration that in a natural way generalizes this subbundle here, you pretty quickly understand that, that the quantity which is important is the slope, the ratio of the degree to the rank. And some other, if you have a bundle of a higher slope and you take the quotient, then the quotient is going to have a lower slope. Okay. Yeah. Well, I mean, in general, it's going to be the highest degree, so to speak, the highest degree subsheaf. But if you take the highest degree subsheaf, I mean, it's not completely clear, is that well defined? I mean, it's not clear that there's a unique sort of subsheaf of highest degree. When you try to make the proof, what becomes unique is the subsheaf of highest slope. I mean, the largest subsheaf of highest slope, basically. If you have 2 different subsheaves of some same highest slope, if you take the sum of those 2 subsheaves, that'll be the same or even higher. I mean, yeah. If that's the highest slope, it'll have that same slope. Okay, let's see. So that's harder now. Riemann filtration. Okay, so No, it's just what it is. Yeah. I mean, it's not going to be bigger than the rank because each piece has rank at least one, but it could be anything. As you can just see from P1, I mean, you can quickly make examples with any type of harder Gaussian filtration you like just by taking direct sums. You can also see why you want to take the slope. I mean, if these all have the same ends, then that's the slope n. And that's not going to degenerate. I mean, that's not going to do this anymore. When you make things jump, two things can collide together and take the average of the degrees, you might say. It turns out that you can't go in the opposite direction. You can't turn, so stability is an open condition. If you start with if E0 was like that, then all the neighboring E's also have to be like that. That's another property. I could say here, semi-stability, these are open conditions. In some sense, I mean, having a section is a closed condition, right? And this is going to have an extra section. It doesn't really have an extra section. It could have an extra section. I mean, if it was O of -2 plus O of 2, then it would have 3 sections, and this will only have 2 sections. Because in this case, it doesn't have an extra section, but it's sort of, all the sections kind of, right? Here you've got 2 sections, and here you also have 2 sections, but they coincide. Okay, so that's a closed condition. So the next thing I would like to point out as sort of evidence as to why this is a good condition to look at is what's called Langton theory. So if we want to have a nice moduli space, ideally our moduli space would also be compact. To have a projective thing once we get it to be set, well, before I get there, I should state the proposition for separated. So well, it allows us to do that. But that's, I think, maybe partially what I was just about to say here, actually. So what do we know? So separatedness. Well, yeah, sorry, even before I get to separatedness. Right, if we have a map, and this is maybe part of the, of course now many of you will be saying, okay, this, we can see what direction this is going. I'm maybe not going to say that too much, but maybe at least not before Thursday. But there's this general thing called the notion of Bridgeland stability condition, where having a Harder-Narasimhan filtration is one of the main properties. It's just that you define the slope has some different form. It might have a different formula, but you'd still have to have this as like one of the main properties. And maybe I should have said that one main property is that you can't have a map. There exist no maps E into E prime if E is semi-stable of slope mu and E prime is semi-stable of slope mu prime, and mu prime and mu is bigger than mu prime. There's no maps from a higher slope thing to a lower slope thing. That's just generalizing what we saw here, that there's no maps from O of 1 back to O of minus 1. Okay? Or you couldn't say that about degree, right? I mean, right, you could have a bundle of degree 1, just O of 1, and a bundle of degree 0, right? There's going to be a map from a bundle of degree O of 1 to a bundle of degree 0. Okay? And even if you have semi-stable things, if you look at the degree, that's also not going to work that way. Okay, so now we have separability. Which is that suppose Suppose we have given two families, which, let's say, roughly speaking, are parameterized by a disk. So if you want to work in the algebraic category, we could say the spec of a local ring or something like that. Suppose we're given two families of bundles, so families of bundles on X. So, technically, this is really going to mean bundles on X across the disk. And suppose that E, and for all t different from 0, ET is isomorphic to E prime t. Okay? Then suppose that E0 and E prime 0 are stable, then it implies that they're the same. Okay. The proof of that is easy. The proof is that we have a map for the hom from E t into E prime t is semi-continuous. As a function of t. And it's non-empty, so it has dimension right. It's just by general theory, since X is compact, for the projection down to X, down to delta from X cos delta of E dual tensor E prime, that has a semi-continuity property, which says that the space of morphisms only jumps up. But also by hypothesis, we have morphisms for all values of t that are different from 0. So that means there exists a morphism at t equals 0. So we have a morphism E 0 into E prime 0. Okay. So this has to factor through the image, right? Okay. But the image is a subbundle of E prime 0. So since E prime 0 is stable, the degree of the subbundle, well, either it's equal to E prime 0. So if F equals E prime 0, then we're done. Then it's isomorphism. Maybe skipping a little step, but you experts can fill in. Either it's equal to E prime 0 and then we're done, or if it's different from E prime 0, then the slope of F has to be strictly smaller than the slope of E prime, of E prime 0, which is equal to the slope of E0. The degree, of course, is the same, right? The degree of a bundle doesn't change in a family. So the degree at 0 is the same as the degree at t. They're the same. So they have the same slope. But the slope of F is strictly smaller than the slope of E prime 0, so it's strictly smaller than the slope of E0. So that means if we take the kernel, right, and when you have an exact sequence, then if the slope here is smaller, then the slope here has to be bigger. But this contradicts stability. Okay? So that's the proof of that. Okay? Now we can make a better statement, but the proof is more difficult, and I'm not going to attempt to do it here. It's elementary too, but I'd probably get it wrong on the blackboard. So more generally, if E0 and E prime 0 are semi-stable, then we can conclude that they are S equivalent. which is another way of saying that would be Jordan-Holder equivalent. So in other words, let me just quickly write this down. Okay, Jordan-Holder equivalent for semi-stable bundles means that if we take a filtration such that the quotients are stable, so if you think about it, that exists by the definition of semi-stable. If you take a filtration such that the quotients are stable on both sides, then they might not be so the bundles might not be the same, and the order of the pieces might not be the same either. But what is true is that the direct sum of the graded pieces are the same. And these are called the semi-simplification. So some of you might be familiar with this type of thing in the context of representations of a discrete group, for example. It's the same thing. If you have a not necessarily irreducible representation, then it has a semi-simplification, which is the direct sum of any Jordan-Holder series. And that's the kind of unique thing that we're talking about here. That really, in fact, corresponds exactly to that in the correspondence, to the non-abelian Hodge correspondence between bundles and representations. So in any case, what you might say is that we have to, as they say in French, mettre de l'eau dans son vin. For the moduli problem, so the notion of semi-stability is not a wonderful solution to the moduli problem in the sense that we're going to need at some point to quotient out by this equivalence relation. Okay. But at least it's better than the unstable bundles. The unstable bundles, like anything goes. Let's see. So that's separability. So the conclusion is that if we take, so now we can hope to define a moduli space of semi-stable bundles. So if you, let me insist on the fact my example here, which I didn't actually prove, but this example showed that if you don't require any kind of semi-stability or stability, then this is just not true. You can have the same family at ET different from 0 that has two completely different limits. Okay. But we can hope to define a moduli space of semi-stable bundles with the property that points correspond to S equivalence classes. Of semi-stable bundles. Okay. Now, what about, but you might say, okay, but maybe this was maybe we could make a different condition, like a stronger condition. Maybe we could ask that the sub-bundles actually have slope even smaller than, much smaller than the slope of the bundle, or like, less than the slope of the bundle -1 or something like that. I mean, maybe we can require something smaller. That wouldn't ruin this property. So to see why stability is sort of you might say, the ideal compromise here, we'll just notice that if we made a stronger condition on subbundles, and people look at that. I mean, there's in the context of connections, it's an interesting question about what are the possible slopes of subbundles. But if we make a stronger condition, then we're going to be throwing out some points of the moduli space. So let me just point out that if we have stability, then in a certain sense we can be guaranteed to sort of capture all the points. So that's Langton theory. What does Langton theory say? Langton theory says that if it's some kind of compactness of, it basically says that M is compact. So you might say, Langton theory says we can tell that M is going to be compact even before we constructed M in the following sense. So the proposition, or the theorem, is that if that given a family ET given a family of bundles ET for t different from 0, then if the ET are all semi-stable, let me just insist on the fact that, of course, the rank is going to be the same, and an algebraic family, the degrees are all going to be the same. By family, I don't just mean a collection of bundles. I mean, an algebraic family of bundles, or at least an analytic family of bundles. Then there exists a way of filling it into E t for all t, such that E0 is semi-stable. And E0 is, so this is, E0 is unique up to E0 is unique up to S equivalent. And this is Langton's theorem. Let's just briefly see what type of construction is going to be happening here. Let me not get slowed down by forgetting steps of the proof, okay? So idea of the construction. The idea of the construction is that just choose any way to some extension E prime to a bundle X cross delta. So I guess we probably need to make some condition about the family being algebraic as we go towards 0. So sorry, I wasn't supposed to do that. So we assume the family is meromorphic. We assume the family is meromorphic, which just amounts to exactly saying there exists an extension. Okay. By the word meromorphic, that means there exists an extension. I'm just kind of cheating there, but okay. So we're just we'll be assuming that there exists some extension of the bundle to a family to a bundle. Of course, if we're in the algebraic world, so if delta was spec of a local ring and we were talking about schemes and stuff like that, then this is always true. This is a surface. So on a surface, you can always a torsion-free sheaf. You can always make it reflexive, and then a reflexive sheaf is automatically a bundle. And in the higher dimensional case, we can do the same, all this stuff in the higher dimensional case. In the higher dimensional case, of course, we're not going to get a bundle, but we're going to get a torsion-free sheaf here. We'll get a reflexive family on X cross delta, but the fiber is not necessarily reflexive. The fiber is torsion-free. Okay. That already showed up in Sarbessoir's talk where you had M bar was the torsion-free sheaves on the boundary of the moduli space. Okay, so, but for curves, there's no torsion-free stuff on the boundary, except maybe as maybe biology will be telling us that when you go to a degenerating curve, but here our curve is just fixed, smooth. Okay, so we choose some extension, but then of course E prime is not going to be semi-stable. But then we look at F1 inside E prime is the maximal destabilizing subsheaf. In other words, the first term of the Harder and Riemann filtration. Okay, so maybe this answers a little bit Dan's question. Here's where we're really going to be using the Harder and Riemann filtration in a more serious way than what we did for the separability. Okay. So we take the first term of the Harder and Riemann filtration as 0, yeah, sorry. Yeah, I mean, of course, this means that E prime t is equal to E t, or t different from 0. Technically speaking, we assume we have an isomorphism between our given family and E prime restricted to x cross delta minus 0. Okay, so then what do? Then we make a modification. We can look at the sheaf supported on the central fiber, E prime 0 mod F1, and take the kernel on the total space of E prime mapping to that sheaf. Okay. Then there's two cases. Either eventually the maximal slope decreases. So we modify to E2 and then we continue. So here's some calculation that you need to do. Let's not do that here. But what happens if when we make this modification, then we get a new bundle. In the new bundle, maybe I can say, I mean, E2 0 has a map to E prime, sorry, has a map to F1. And the kernel is E prime 0 mod F1. Twisted my minus the fiber, but the fiber is a trivial bundle. The O of the fiber is a trivial divisor on this thing. Right, here I should really put minus the divisor, which is the fiber. But that we can trivialize that thing by using the uniformizing parameter. So now we have a bundle which is an extension. So this has all the rest of the Harder and Riemann filtration. Okay? And this has the top level of the Harder and Riemann filtration. So the maximal slope, if you think of it, what can a subsheaf here look like? Okay, if it maps in a non-zero way to here, then what kind of semi-stable or stable subsheaf here look like? If it maps in a non-trivial way to here, then the slope has to be less than or equal to the maximal slope here. If it maps to 0 here, then the slope has to be even smaller because this is the rest of the Harder and Riemann filtration. Okay. So that's the new fiber. Okay. So what might possibly happen here is we might still have a subsheaf that maps isomorphically to this one. Okay. So even if we have, maybe I should say the max slope and or the rank of the max. I mean, what you really need to do is make decreasing in lexicographic order the maximal slope and then the rank of the maximal piece. Okay? So if our maximal piece of this thing maps to here but was not an isomorphism, then it would have a smaller rank, and so we would have decreased our invariant. Okay? What might happen is that the maximal piece here maps isomorphically to here. So it stays the same size and stays the same slope. Okay? So one case is where eventually the whole thing goes down a little bit, and then we keep doing the operation, and eventually we get to a semi-stable. Okay? Or the other case is where it never goes down. But then you have to imagine a little bit more technical algebraic geometry stuff here. But if it never goes down, if you think about it, what does that mean? That means that we're going to have a whole collection of subsheaves up to all orders, which look isomorphic to this F1. Okay? So kind of to all orders, we're going to have subsheaves of our family bundles, which look isomorphic to this F1. And when we put those together for all orders, we get a formal family of deformed subsheaves, which sort of projects out away from the origin. And if that's true for up to the infinite order, then we'll get a formal subsheaf, which contradicts stability of the whole family. Okay, in that case, we'll get a subsheaf of E prime restricted to like spec formal of C. Something like that. And then you have to apply like Gaga and stuff like that to go from formal subsheaves to actual subsheaves. But then you get a subsheaf of E prime at T different from 0, contradicting stability. Semi-stability. Okay. So is that sort of semi-clear at least? That's the idea. The idea is that either, when you do this process, either your invariant goes down, and then if it keeps going down, then eventually it gets down to 0, and then eventually you don't have a hard-order Riemann. The hard-order Riemann filtration is trivial, and then that means it's semi-stable. Or if you get to a place where it stops and it just stops going down, then since that goes all the way out to infinity, that meant that you actually integrated out to a subsheaf that was contradicting stability on the generic fiber. Okay? And so that's the proof of Langton theory, which tells us that, in principle, we know that this is going to give us a compact moduli space. So that's all stuff which we've done without even talking about how to construct the moduli space. So I'd claim that that's, I'm sure you can do more, but that's kind of my list of intrinsic reasons for using stability. Okay. Now, what about the GIT? So then that ends that section. So the next section is construction of the moduli space, so GIT reasons. To look at stability. So this is basically Mumford. Okay, so now how are we going to construct the moduli space? So now we have some idea that we would like to make a moduli space. Well, I guess you should probably maybe say that probably by following along. I don't know if anybody's really written this up. I think Janos Kolar and the people who do higher dimensional Mori theory and stuff like that, they did actually pursue this, the idea of looking at this intrinsic sort of definition of how to look at constructing moduli space and use that to actually construct the moduli space. I'm not sure if anybody's done that for bundles. I guess in principle you probably should be able to. That would be sort of following Artm's method to its logical conclusion as to how to construct like an algebraic space of bundles or something like that. I think you probably could do that. I don't know if maybe somebody has. But so Mumford's theory was not that way. This was to use projective geometry. Okay. The idea to use projective geometry is so we like to use the fact. So what is projective geometry? It really means that on X. Well, so what did Kolar and these people do? They constructed a moduli space of like varieties of. I think Kolar first gave a construction of the moduli space of curves this way. Then they've been doing that for higher dimensional varieties, just by Artm's method. So you say, okay, let's just look at the moduli space. Look at the moduli functor, and then try to create an algebraic space, for example, and then try to like create a positive ample line bundle on that space using the Hodge bundle, for example, in the case of moduli of varieties, and get a projective variety that way without ever doing the GIT version of stuff. So I'm saying, I mean, you probably, by combining Langton theory and the separability and, Korenishi spaces and stuff like that, I guess you could probably try to do the same thing for bundles. You'd have to figure out what's your determinate line bundle. This might actually be done in Huybrecht-Lane's book. They have a section about determinate line bundles. Yeah, maybe, yeah. I'm sorry, maybe it's just my ignorance of the literature, possibly. Anyway, but so what I like to talk about here, and of course historically this is what came way before, is the projective geometry GIT construction. Okay. Yeah. Yeah, I mean, of course, the problem is that if you just do that for an algebraic stack, you'll get an algebraic stack, and you might be able to say, by boundedness, if we look at semi-stable, if it's bounded, then we have a finite type stack and stuff like that. I mean, but you'd have to do the local picture that says why you can scrunch together all the semi-stable ones that are S equivalent, get an actual space. I mean, as I said, that should be doable, but that's not what we want to do now. I mean, that's not what I want to do now. Okay, so what does projective geometry basically mean? It basically means that on X we have a line bundle OX of ample line bundle OX of 1. And so if we're given a bundle, well, there's a lemma which says that the set of semi-stable bundles is bounded, is a bounded family. Which, if you know what that means, you'll know what it means. If you don't know what it means, it just means that the next statement I'm about to make is actually true. Okay, so there exists an N Right, so what's P of n? P of n is the Hilbert polynomial, is what I was saying. P of n is equal to degree of E of n plus rank of 1 minus g, which is, I guess, the degree of E of n is going to be the rank times the degree of n. So, I mean, it's a polynomial of degree 1 in n, basically. But it's the Hilbert polynomial, which is just the dimension of h0. So part of the statement here is that the h1 of E of n is 0 for a high enough value of n, uniformly in all of the semi-stable bundles. So this bounded thing means that we can choose a single n with the property that the h1 of E of n equals 0. So that h0 is just given by the Euler characteristic, and that the map, as a natural map, this is really h0 of E of n tensored with O x of minus n. Okay. We have a natural map like that, but this is isomorphic. If we choose a basis here, this is isomorphic to O of minus n, P of n. P of n. P of n is P is the Hilbert polynomial of E. Okay, so sorry. P is the Hilbert polynomial, so it's just the dimension of h0, given that h1 equals 0. Okay. Yeah, so maybe I should, let me write that down again here. That's an important, obviously. This is the main starting point of the construction. we have H0 of E of n. Of course, E of n means E tensor over OX with OX of n. And here we're working in the algebraic geometry world where E is a algebraic bundle. Okay. So H0 of E of n tensor with, over C, I guess, with OX of minus n projects onto E. Okay. It means that E of n is generated by global sections. Okay. This is the statement that E of n is generated by global section. Okay. And so if we choose a basis, then we get C to the P of n tensor O of minus n to the P projects onto E. This is just equal to O of minus n to the P of n. Okay. So this is the basic first step of the construction of the moduli space. So this is an intrinsic property of E. Okay? Given any bundle E, you always get this map. This is not an intrinsic property of E. This depends on this intrinsic property of E, this intrinsic thing attached to E, plus the choice of a basis. Okay? Choice of a basis for this vector space. Then the idea is just that the moduli space is going to be the set of quotients. Let's call this quote. Divided by GL, so let's say SL of P of n. So a little side observation is that if we scale the basis here, then we can absorb that by doing a scalar here. So that's not going to change things. So we can, instead of dividing by GL of P of n, we can divide by SL of P of n. Okay. And the quote scheme there's maybe a little technical, maybe there's a little extra, maybe a few extra decorations that we should put here, but roughly speaking, it's a set of quotients like this, such that E is semi-stable, and such that this map was the one we started with up to isomorphism, which is to say that map induced an isomorphism between C, P, and N here. Okay? So that's a perfectly well-defined scheme, and our moduli space is going to be the quotient of that scheme by the set of change of bases. Because what we said here is that if we have a bundle E, then if we choose a basis, we get a point inside here. Okay. If we choose a basis, we get a point here. And the GIT construction of the moduli space is to say, let's make a quotient by a group action, which is just the choice of basis. So we have a group that's acting, and we just want to make a quotient and say that the quotient is the moduli space. Up to a few maybe details I'm probably forgetting here, but up to a few details here, it should be clear that there's a clear that there's a unique point in this quotient corresponding to every semi-stable bundle here, if the quotient exists. And then Mumford's GIT this tells us criteria for being able to make this quotient. In other words, what type of condition, I put semi-stable here because that's what we should really do, but what type of condition should we put on the bundle in order to fit into a variety such that we can actually make the quotient? So depending on how we choose our condition here, that's going to expand or contract the variety here. That's going to make it possible or not to choose the quotient. So what should we do? We're trying to do projective geometry, so we should embed this quote scheme inside some projective space. Okay? And so you might say our first idea. And so I think this is what was used by Mumford, but maybe this is probably unpublished as far as I know. Maybe Gieseker. Then I think, if I'm not mistaken, also Nitsuri. Maybe there's a couple of other ideas also. Nitsuri for Higgs bundles. I might be mistaking. There's a couple other techniques here, but let's just do what's the first type of idea that you might think of to try to embed such a thing inside some projective space? Is let's choose lots of points. Let's call this speeding up here a little bit. So at each point, we get a map from the quote scheme. Sorry. At each point, if we have a quotient, then we get just the quotient at that point, which is just a point in the Gauss-Monnian, okay? Then this is going to be embedded by Plöcker coordinates into the projective space of lambda to the r CP lambda. Well, maybe there's a dual there or something, okay? Then we take the product over all the points plus the Veronese. Okay. So this just says that we're going to measure a quotient by what it does at all these points. Okay. At each one of these points, we get a point in the Gauss-Monnian. Okay. So we can just do standard algebraic geometry to measure, and we get a projective embedding. Well, I mean, I'm fuzzing over lots of details here, but roughly speaking, we get an embedding. Sorry? The Veronese. Right here we have, for each point, we have a point in the Gauss-Monnian. We take the Plöcker embedding, so we get a point in projective space. And we have that for a bunch of different points, so we should take the Veronese embedding for all those different points. So this is getting kind of big. But let's hope understandable still. So we embed the quotient scheme into PM, and this is SL of P of N equivariant. So we're reduced to the question of how to, so we get the question is how to make a quotient of a subvariety of Pn. If you think about, I mean, this PM is going to be a gigantic tensor product of these spaces over all the different points, okay, and these, but SL of P of N acts on each one of these. So it's going to act on the tensor product. So how do we make a quotient of a subvariety of PM? So basically it means that we have our group G. This is the big group, it's not the structure group, which is SL of P of N. Acts on some C to the M plus 1. Okay? And the basic idea is that a semi-stable point, let's say, well, this is kind of very rough, but a semi-stable point is basically one whose orbit doesn't touch It doesn't approach, let's say, the origin. Okay. And then we can make the following kind of quick and dirty substitute for reading GIT, which is not all that long a book anyway. But so there's a one parameter family, one parameter subgroup criterion, and so on. Let's just kind of do a quick thing. I guess, shall we say, a physicsy type of thing to do to make the quotient. So let's just look at let's just try to take the point closest to the origin. Okay, so try in each orbit. Let's look for points closest to the origin. Okay. So every time we have an orbit of our action, let's look for a point that's closest to the origin. Okay, this might not exist. If it doesn't exist, then we have to jump to a closed orbit, right? If we go along our orbit and we try to approach the origin, well, of course, if it's unstable, then it shouldn't approach the origin. So it's going to have a closest to the origin limit. That might be in a different orbit. This is just in brief, very briefly. This is the explanation for S equivalence. This is why you might have orbits whose actual point is not in that orbit, but it's in the closure of the orbit. And it's going to be in a closed orbit, which is like the unique closed orbit in the closure of the orbit. Okay. But so by jumping here, we're going to get to a place, to an orbit where there exists a closest point to the origin. If it exists, then the orbit, the G orbit in C to the m plus 1 corresponds to U, let's say SU of P of R, P of N. Corresponds to an S to a unitary, so a maximal compact. Okay. Okay. So if you think about it, so of course G doesn't preserve the distance, but the maximal compact of G, since we're just talking about change of bases at the origin, right? Our vector space is some big vector space, but which just came from the SL P of N action on C to the P of N. So the maximal compact is going to preserve a metric here. It's going to preserve a metric on the whole gigantic space. So we can just look at the closest point to the orbit. That's going to define a compact group orbit. And these closest points, these are what's called the zeros of the moment map, if I'm not mistaken. What does that mean? It just means those are points where the first variation of the distance to the origin is 0. Okay, so it's just a linear condition. This is a theme which comes up like in parabolic bundles later also, which is that delta of distance equals 0. As you move in the orbit, you just say the derivative of the distance to the origin equals 0. That's a linear condition. And that's called the zeros of the moment map. And that's going to define the subspace of all points to which are going to be their closest points to the origin in their orbits. So we can look at that, so we can impose that condition and then divide by k. So we take this thing, and the set of points satisfying this thing, then divide by k. This is a nice topological quotient. We mod out. By compact group, okay. And stable points are polystable points are the ones which have a closest point to the origin. Semi-stable points are ones whose closure contains a polystable point. And unstable points are ones where the thing maps arbitrarily close to the origin, so we don't want to do that. Okay? And this functional, so log, I guess log of distance of our point. This is the Kempf-Ness functional. Yeah. Log of the norm of the point. I mean, distance to the origin, maybe. Log of the distance to the origin, if I'm not mistaken, is the Kempf-Ness functional. Like that, I mean. When you have a semi-stable point, as you try to get closer and closer to the origin, you're never going to get to the closest point to the origin, but it's going to have a limiting point. That limiting point is going to be in the closed orbit. Or at least, I mean, it might be jumping to a less complicated semi-stable orbit, but then you continue. But in the end, when you finally get to the closest point, that's going to be a point in the closed orbit. That's a little bit special to the case of bundles. I mean, I'm not sure that's really, I mean, I guess it's true in GIT for linear actions on a space. I mean, it's not, it's true under some hypotheses which work in our case in any case. Okay, and so now what about the condition of stability? The condition of stability says that what does it basically say? It says that lack of stability by either maybe following through this a teeny bit more, but maybe we don't have time, or by looking at this one parameter subgroup criterion. Lack of stability corresponds to having a subspace of this big space that accounts for too small a piece of bundle. Right. In other words, we can make a we're asking for a point in the group SL here, right? So we can make a transformation that expands along certain directions inside W, inside C to inside here. Or we can make a group element that expands along certain directions and contracts along other directions. Okay. Then we map it into. Then we look at what it does inside this line here, which we got by first taking the determinant at each point and then producting those all together. Okay. If the maybe I guess contraction directions overpower the expansion directions inside here, then that point is going to be getting arbitrarily small as we go to the origin. And well, you have to do the calculation, but what that comes out to saying is if you have a subspace that accounts for too small a piece of the bundle, which is to say we look at a W tensor O of minus n surjects onto a subbundle, what is it going to say? It says that the rank of the subbundle is overly small, so that So that if we take dimension W, the proportion of dimension W to the dimension of the whole space, P of n, is bigger than the proportion of the rank of F to the rank of E. So if you have a subspace here, which is kind of too big, that goes to a smaller thing here, then that's going to be the phenomenon that creates a piece of the orbit that goes towards the origin. Okay? And we can rewrite this as saying dimension of W divided by rank of F is bigger than dimension P of n divided by the rank of E. And this is basically the degree of E. This is basically the degree of F, right? Because W is going to be a subspace of H0 of F of n. Let me write that down over here. Yeah, this is reworked a little bit. So if you have a one-parameter subgroup, for example, I mean, what Mumford says is that if you have a point, if the origin is in the limit of the orbit, then it's actually going to be in the limit of a one-parameter subgroup that goes to the orbit, that goes to the origin. There's going to be a one-parameter subgroup of the group that actually takes you to the origin. That one-parameter subgroup is going to correspond to a whole decomposition of the thing. And then you sort of turn that around a little bit and kind of work out the decomposition and just turn it into a single subspace, which is like the worst possible piece of that sub-thing. Okay. Once you do that, then you get to this version of the criterion. But you can also do the same type of thing here with the metric thing. Anyway, but you get to a criterion that says that if they might say the bad case for having where you're going to have the origin in the closure of the orbit is the case where you have a subspace of the space Cp of n with the property that it accounts for too small a piece of the bundle. Okay. And you might say maybe it's too big a piece. I mean, the calculations go in a certain direction, not the other direction. That you might say. But this is what it turns out to come out to, which is that the subspace here accounts for too small a piece of the bundle, which is to say, like smaller than you would expect, right? You might have a subspace here. You could, of course, choose a smaller subspace and a bigger bundle. That's easy to do. What's hard to do is to have a big subspace and a small bundle, right? What it means is that you have this big subspace, which at all the different points is going to be all sort of aligned in the wrong way. Okay.
There's some way to see with like sort of pure thought without a calculation that this phenomenon is the reason why you
that's what I was hoping to say, but we're running out of time here. And I think if you think about it in these terms, right? If you take the subspace, you can think of the subspace. I mean, if you have a subspace, you can make a contraction in one direction and an expansion in the perpendicular direction along that subspace. So you can make a family of group elements that way. Then you look at what does that family of group elements do to this log distance to the origin, measure over here. Right, so you have to look at what does that family of contractions going to be doing. I mean, let's like look at a single subspace, right? So if we sort of expand in one direction and contract in the other direction over here, what's that going to do on the determinant? I mean, on the lambda r, I mean, it's going to sort of expand those are the directions which, I mean, if you take this, so you like take the unit ball inside C to be the n and project it into the quotient space, right? Where do we have? Right, take the unit ball inside here and project it over to here. Okay, then what's the determinant of that projection, basically? Okay, if you think about it, if it's sort of balanced, so if you divided this into two pieces and sort of expanded on one piece and contracted on the other piece, and those two pieces went to pieces of the same size here, then everything would be happy. There would be no problem. But if one of the two directions, I'm not sure which one, but if one of the two directions accounts for too big a piece here, and the other expression part accounts for too small a piece here, then you're going to have some multiplication of the determinant. And if that same subspace does that for all the different points, then that's going to create the problem. I mean, that's the, as I said, I'm running out of time to actually do that here, but yeah. Anyway, but so this is what turns out to happen. So this is the calculation which tells you that that we're interested in the notion of stability, because the dimension of W is basically the Euler is going to be at least bounded by the Hilbert polynomial of F, whereas the dimension of P of n is the Hilbert polynomial of E. Okay? So the bad condition is when the degree of F is too big with respect to the degree of E, but divided by the rank. Okay? How are we doing? Probably should be stopping here, right? Yeah. Let me just finish by just stating the Narasimhan-Seshadri theorem. So that's the, maybe we'll start next time with that, with the connection version of this picture. So we'll go a little over time into tomorrow's talk, I guess. Okay, so then we have the differential geometric, or connection. Differential geometry or gauge theory motivation is the Narasimhan-Seshadri theorem. Which says that the E is, say, stable, maybe of degree 0. If and only if it has a structure of irreducible unitary flat bundle. So I'll be testing this more next time, at the start of next time. But Narasimhan-Seshadri's proof was a deformational proof. Basically saying that the tangent space agrees on these two sides. In that sense, as we've already seen, we have the separated property. I mean, this is, of course, in their paper. The separated property, and the fact that, in fact, the unitary representations are automatically compact. So you don't really need the Langton theory for Narasimhan-Seshadri, but you need the separated property, and that comes from their paper. That plus the local calculation about the tangent space tells you that these are going to be the same. There's a natural map from here to here. It tells you that that's going to be an isomorphism. But so then the whole subject, like the subject, I mean, it has to be said the whole subject was very dormant for what, 20 years or something? When was Narasimhan-Seshadri, like around 1960 or so? Until like 1980, 81, and then like the mid-80s, so 20 or more years. Although, does somebody know? I don't know, which is different. But if
anyone can find a justification for semi-stability from that point of view.
Well, I mean, something has to be said for the orbits that approach to the closed orbits somehow or other. So I guess that would be the answer. I think so. Yeah. I'm not sure, but I think so. Yeah.
I mean, there is a Kobayashi look at a sort of approximate Einstein condition, right, for semi-stability. So, but which is an approximation, So, but is that a
I think that
it could be a justification somehow.
I mean, I think in the infinite dimensional picture, you're also going to have orbits that approach to the polytable, and those are going to be the semi-stable, which I think that comes down to saying that.
Any other questions?
Did you mention that it also has a kind of a code scheme mod out by quotient of a code scheme structure?
Yeah, I didn't really do Higgs bundles yet today. Yeah. But yeah, you can say that.
Any other questions? So I had a question. You motivated stability from two different points of view, right? The Artm filtration was the starting point for the first approach, and then you had this GIT approach. And the two are connected in this case through the picture you described. But is there some, do you think there's some intrinsic way to connect the two in general? I mean, the two look like a priori very different ways of thinking about stability.
Well, I mean, as you know, there's there's this notion of bridge instability condition more generally, and I guess you can hope to. But I don't know if anybody's really done that. I mean, you could try to say, in general, if you have a derived category and you have a bridge instability condition, you should be able to construct a moduli space of objects satisfying the stability condition or something like that. And that the considerations here should be holding for that case also. I think the kind of Kempf-Ness functional and stuff like that. I'm gathering, but
so bridge instability is for like triangulated categories. So you have this additional complication of being a triangulated category and things like that. If let's say just in the abelian category situation,